This is segment 1 of topic 2.3 on work, energy, and power. So let's talk a little bit about work. When we talk about work in physics, we're talking about transferring energy. We're talking about one object giving or taking energy to another object. So when you do work on something, you're changing the energy associated with that particular object. Mathematically, work is the product of the force times the displacement times the angle between the two. And it's important here to remember that both force and displacement are vector quantities. We measure work in units called joules, and 1 joule, and we can maybe get this from the equation, is newtons times meters. Okay? Which breaks out into our fundamental units, kilograms times meters squared per second squared. And let's take a minute and look at this equation a little bit more and what it means. So work is equal to force times displacement times the cosine of the angle between the two. And so what that means is that if we have a box, and we'll just use a box for simplicity, and we exert a force on it in this direction, and we move it or displace it some amount d, the angle here between the force and here, if we draw our displacement vector, here's our displacement, they're in the same direction, and so the angle here is 0. And we all know that the cosine of 0 is 1. And so what that means is that when the displacement of the object and the force are in the same direction, the work done is at its maximum. If, however, on the other hand, let's say you're walking around and you're holding a box in your hand. You're exerting an upward force to hold the book up, to maintain its upward position, and let's say you then walk some distance. You displace the box through some displacement or some distance. So now the angle between our force and our displacement is 90 degrees. The cosine of 90, as again I'm sure we all know off the top of our heads, is 0. So if the angle between the two vectors, the force and displacement vector, is 90 degrees, this force here that you're exerting upwards is not doing any work on the object. It's not changing the energy. And then of course we can have any component in between, and if we look at a situation where it's somewhere in between, let's say you're pulling a box with a string, and that string is at some angle. Call this angle theta, and the box is moving in this direction, so the displacement is in this direction. Well, if we look at our force triangle and we were to break it up into vectors, what we see is that f cosine theta is equal to this x component here which is the component of the force that's in the same direction as the displacement. So what this boils down to is only the force, or the part of the force that's in the same direction as the displacement, is actually doing work on the object, is actually changing the energy associated with the object. Now, to go along with that, we can look specifically at the work done by gravity. And relating to that, to what we just talked about, if we're sliding a box along the floor, say we're pushing it, doesn't really matter how it's moving, but we're exerting some force in this direction, and the box is moving from point A to B to C to D, our displacement here is to the right. Somebody here, our little guy here, he's doing some work on the box, but when we're talking about gravity, gravity is directed down towards the earth. And so the force of gravity is acting at a 90-degree angle to the displacement of the box. And so we said before, cosine of 90 is 0. So if something is sliding along the ground, gravity is not doing any actual work on that object. But if the object moves vertically, so up or down, now gravity is playing a part. Now gravity is causing a change in the energy. Gravity is doing work on the object. And that work if we remember, work is equal to FD cosine theta, and force of gravity, the force of gravity is equal to the mass times the acceleration due to gravity. Then we have the work done by gravity equal to m times g times the change in height, which is where this comes from. Now, work can be positive, work can be negative. If the object is falling, so the displacement is down, then the angle between the force and the displacement is 0, and so the cosine of 0, as we said, is equal to 1. And that's where the positive mgh is. So, and you think about when something falls, as gravity acts on it, it accelerates. So gravity is increasing what we call the kinetic energy, and we'll talk about that in the next set. If, however, on the other hand, let's say you pick up a box, and the box was on the floor, and you pick it up, you have to exert some force, you have to do some work on it, but gravity is acting in the opposite direction. And so the angle between the force of gravity and the displacement is 180 degrees. The cosine, we'll remember, of 180 degrees is equal to -1. And so if the force and the displacement are in opposite directions, you actually have what we call negative work. And so when you lift an object up off the ground, you are doing positive work on the object because the displacement and the force are in the same direction, but you're not the only thing exerting force on it. There's also gravity acting in the opposite direction, which is doing negative work. Now, gravitational work is what we call path independent, and what that means is that it doesn't matter how it gets from A to B. It doesn't matter the path it takes. It doesn't matter if we look down here, if it does something like this, up and down, up and down. The only thing that matters is the net change in height. The only thing that matters is the net change in height. Now, when we have some type of force like gravity, gravity acting on an object is a constant force dependent on the mass of the object, but not all forces are constant like this. If you push a box, it's rare that you're going to be pushing it with the exact same force the entire time. Maybe as you wear out, you push with less force. There are other examples, things like springs. These are forces that are non-constant. They vary with time. And so it's a little bit different situation there. When we have forces like this, we can still find the total amount of work done, but we can't do it with just a simple equation. If we go to our graphical analysis and we were to graph the force versus displacement, okay, notice we're talking about a time varying force, but we're graphing force times displacement. Okay, it's a force that varies over the course of the application, so we call it a time varying force, but when we graph it, we're going to graph force versus displacement. Because here, if we have a uniform force, something like that, we can see that we remember that work equals FD. FD here is simply the area under the graph, the integral. Right, so there we go. There's our total work done. Well, this applies to all graphs of force times distance. The integral of a force distance, or a force displacement rather, graph is the total amount of work done, or looking at it another way, it's the total change in energy. If we have something like a spring, which has a linear change in the magnitude of the force, there's a direct relationship between the displacement of the spring and the force applied, we get this nice graph that looks like this, which, if you look at it from a geometric standpoint, we see it looks like a triangle. Area of a triangle is 1/2 base times height, so if we apply 1/2 base times height, or FD over 2, we get the area under the triangle, which gives us the amount of work done by that elastic force.